Okay, hi. Once again, we're going to do day 2 of this week, and I want to show you today a little bit about how to work with ease and how to use your calculator to help you out with some of this algebra and some of this other stuff. There are some things you can do. All right, so what we're going to do, I'm opening up TI Smart View. We're going to look at the calculator in a little bit. I'm going to share my screen with you so we can do the notes. Where's my screen? There it is. All right, so we're going to talk a little bit today about E and how all that works with these, when you're factoring with it and stuff. One of the nice things about working with E, e to the x, I drew the graph here. The domain of it, you'll notice it goes all the way to the left and all the way to the right. So the domain of it is all reals. So the first thing nice about E is it's defined for all x, so you don't have to worry about where things are undefined. They're not going to be. They're defined for everything. The range is kind of important. It's only good for y is greater than 0 because you have this horizontal asymptote at 0. So that's going to be important because e to the x, it's always positive. It never equals 0, which is important when you're dealing with factoring. Sorry, Smart View's really trying to start up on me. The zeros or the x-intercepts, you'll notice that there are none. This graph never touches or never crosses the x-axis. So again, this is what I'm trying to get at. When you're factoring this thing with an e to the x, it'll never equal 0. So, you know, if I want to solve e to the x equals 0, there's nothing, because if you try to take the ln of both sides, let's do that just to show you. Those cancel, so I get x equals the ln of 0. But remember from our study of logs, the log of 0 doesn't exist, all right? So anytime you have e to something equal to 0, there's no solution to that. So that's going to help us a lot in with our derivatives. They're all no solution. Okay. So here's the thing. When you're taking derivatives and you're going to have to pull out a factor of e to the f of x, you set it equal to 0 to find critical values, right? But there's not going to be any place, all right? Because this is defined for all x, and it's never 0. So we can pretty much ignore that term. All right, so let's show you how this works. I want to find the relative and absolute extrema on that interval. So what I'm going to do is take the derivative. I'm going to have to use the product rule. Okay, so remember that the left term is x squared, and the right term is e to the 2x minus 3. So the derivative of the left would be 2x. The derivative of the right, recall that you take the derivative of the exponent, which is 2, times e to the 2x minus 3. Okay? So using the product rule, it's the left times the derivative of the right plus the right times the derivative of the left, right? So we're going to write that down. X squared, right prime would be 2 e to the 2x minus 3. Let's see, plus the right would be e to the 2x minus 3. And the left would be 2x. So I'm going to go ahead and factor this. You see that they have some things in common. They have a 2 in common. They have an x in common. And they have an e to the 2x minus 3 in common. So I'm going to factor all that out. And when I divide that out, the first term, the only thing I'm left with is an x. And this one, there's nothing, so it'd be plus 1. All right. So here's the deal. We have 3 factors. We have either 2x equals 0 or x equals 0, so that would be a critical value. E to the 2x minus 3, if I set that equal to 0, remember there's no solution to that because e to the x is always positive. So this has no solution. So you can all the time just ignore this factor. All right. Or x plus 1 equals 0. So I get x equals negative 1 as a critical value. So that's easy. So now that I've done that, all I have to do is make myself that table -3, where's my critical values? -1, 0, and 1. And I'm going to plug them, remember, back into the original function. And I'm going to use my calculator to help me with that. Heck, I'll show you. Okay, so I'm going to go in my calculator, enter the function, x² times, where's e? E to the 2x minus 3. All right, and I'm just going to graph it. I don't care what the graph looks like, but then it should show me something I'm interested in. It's really hard. It doesn't really look like those are critical values, but let's go to the table and see what happens. Second table. All right, so -3 is 0.0011. Let's see, -1 is 0.0067. Let's see, 0 is 0. And 1 is 0.3679. All right, so first of all, so the highest value I have is this. This is the absolute max. The lowest value I have is this. So this is the absolute min. Now, I'm seeing from -3, I'm just going to plot these points, sort of anyways. -3 is 0.0011. So like, we're just gonna, it's like here, somewhere low. -1 is 0.0067. So you see that it went up and then it went down to 0, 0. So this tells me that that's a relative max. All right, so that's a relative max. Now, 0.0, this one is an endpoint and it's not an absolute, so we can ignore that, okay? All right, and so really there is a maximum there. It's just the way that the graph was zoomed out, we really couldn't see it. So I'm gonna do a little zoom here to convince you that that was a maximum. I'll do a zoom box, I guess. Where's box? Where's zoom box? There we go. All right, so I'm gonna pick that and I'm gonna make a little box right around where I thought that. That's interesting. The zoom box. Oh, that's right. Okay, we're gonna make a little box. So I'll just kind of enter. I'm just gonna zoom in on a little boxy area and see if I can see that maximum at -1. That's good enough. Boy, really hard to see. All right, so again, sometimes a graph is really, really hard to see. I'm gonna change my window by hand. I'm gonna change Y so that you can see that. So I'm gonna go from, we'll let Y min be 0, 0.0067. So we'll let Y max be 0.008. So that should be good. Okay, and hopefully then maybe, yeah, you can see that maximum now. Because of the scale I picked, it looks, you know, bigger than what it is, but now you can see that maximum. You couldn't see it before. You can't always trust what you see on the calculator. All right, but the calculus will always be right. Okay, things, notice e to the 2x minus 3 did nothing. All right, it's just something to factor out. All right, so some more practice. I don't know if I'll do all of these, but critical values, I'm telling you these are the derivatives. Hey, guess what? We already found them. Now we're going to find the critical values, so we just have to factor it. So when I look at this, I can take out an x, I can take out an e to the x, and I'm left behind with 5 minus x squared. So when I set that to 0, I have x equals 0. e to the x I can ignore. And 5 minus x squared equals 0. So I get 5 equals x squared. So I'm going to get x equals plus or minus root 5. Don't forget there are two answers there. One's positive, one's negative. So 0 plus and minus root 5, okay, are the critical values. So we're going to work with this a little bit. This next one I can factor out a 2. I can factor out e to the x. And I have fractional exponents, so I'm going to take out the most negative fraction. So when I do that, let's see, this one becomes 1 plus 2. And 1/2 minus negative 1/2, you're going to find out that works out to be a 1. Okay, so you can ignore this. X to the negative 1/2, remember that's going to pull this down here and make it x to the 1/2. So it's going to be undefined. The derivative is undefined at x equals 0, so that's a critical value. And where 1 plus 2x equals 0, you're going to solve that and get x equals negative 1/2. So there's two critical values there, 0 and negative 1/2. Don't forget, negative exponent, you're probably going to have some place where it's undefined. All right, so this next one I can pull out, looks like a 3, an x squared, and an e to the 5x. So what do I have left? I have a 5. I have a 2x squared. I'm taking out an x squared, so I'm going to have an x there. There we go. Okay, so again, you can ignore the e. So if x squared equals 0, guess what x is? X is 0. So that's a critical value. And if you solve this other guy, you're going to get 2x equals 5 minus 2x is 0. So you get 2x equals 5, and you're going to get x equals 5/2. Okay? So 5/2 and 0s are your critical values. Okay, more factoring. This guy, what can I take out? I think I can take out as an e to the 5x, so that's the way it's going to be. I may have to do a little bit of algebra here. 6x minus 1 plus, now I took this away, so I'm going to distribute the 5 through. So it's 15x squared minus 5x. Okay, so then I'm going to put all this stuff together. Make it look nice. 15x squared comes out front. 6x minus 5x is 1x. And got that. I got a negative 1. All right. Now, that doesn't factor. So it might have a real root. This is where I'm going to use my calculator. I'm going to see if that has a 0. So I'm going to 15x squared plus x minus 1. Let's see if it does. So clear. All right, and I'm going to put a regular window in there. Let's see if we have any zeros. Yes, we do. They're not nice zeros. So we're going to go find them on the calculator. That's fine. y2 equals 0. Graph. Intersect 5, enter, 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 enter. It found the positive 1.227. You know what? That thing's really symmetric, so the other one's going to be negative 0.227. All right. So same thing here on the top. I can take out a t, e to the t. So I'm left with 3 minus t squared. Okay, e to the t squared, remember you multiply the exponent, so this is e to the 2t. All right, now I want to set things equal to 0. Notice that I can ignore, again, where it equals 0 is where the top is 0. The bottom is never 0 because e is never 0. So there's no place where it's undefined. But so I'm going to work on the top. So to either t equals 0, e to the t is not going to equal 0, or 3 minus t squared equals 0. Okay, so I'm working with this, which is 0, and I'm working with this. So if I solve this, I get t squared equals root 3. T squared equals 3. So t would be plus or minus root 3. So 0 and plus and minus root 3 would be critical values. Okay, let's see what we can work with here. All right, so here, I don't want to cancel this, right? Because it's none over here. But I can take out a 6e to the x. And I'm left with 2e to the x plus 1 minus 2e to the x. Oh, that's nice. The bottom is never going to equal 0. No. I don't think it will, but no, it won't. I don't have to worry about the bottom because e to the x is always positive and you're adding 1, so the bottom's never going to be 0. These cancel. Actually, I end up with a 6 e to the x over 2 e to the x plus 1. The bottom won't be 0. You can convince yourself of that by graphing it if you'd like. And then 6e to the x is never equal to 0. So this particular function has no critical values. That can happen. Okay, so it's entirely increasing or entirely decreasing. All right, it doesn't have any minimums or maximums. All right, so that, we will have an absolute extrema. It's going to be at the endpoints though. All right. I think I'm going to skip. There's nothing exciting about that one. And nothing super exciting about that one. They're kind of both the same thing. So I'm going to let those go since we practiced enough with that. One of the things I wanted to just finish off with is, you can use your calculator to help you locate critical values and things like that. So first thing you can do obviously is graph the function. I mean, you're not going to get any calculus points on this, but you can check and see that what you got matches with what you're seeing or what the calculus is teaching you. So I'm gonna, you can just graph the function x to the 4/3 minus 6x to the 1/3. Now you do have to be a little careful with this, right? Because we showed you that one example earlier where it didn't look like there was a maximum, but it was there. It was just really, really, really small. Oops. And we did this problem earlier, so we'll take a look at it. But here's the graph. Maybe. What? Okay. Oh, there it is. Being really slow about graphing. Okay. So there it is, and we can see that there is a minimum. I can go find it. I think that minimum happened at 3/2. Minimum. Let's see, left bound. Right bound. All right, and they found a minimum at 1.5 and then negative 6.15, which I believe is what we found up there. Let's go back to where that problem was, all the way the back, all the way. Where was it? There it is. Is that it? No. Sorry, trying to find the problem. Pretty sure we did it. There it is. So if you look at this, right, there was our minimum, right, and we didn't have a maximum, so I knew it had to happen at one of the endpoints. I compare -1 and 3, and again, you can do this on your table. -1, was 6 and 3 was -5, so I know -1 is where the max is. So, you know, your calculator can be a great tool in terms of helping you make sure you did the work right. You know, they're going to want to see the calculus, but at least you can always check it. So that's our first option. There is a way to graph the derivatives. If I want to find the extrema, and that was, I think, the one that had the odd, really weird derivative or weird extrema, I can graph the derivative. So I'm going to show you how to do that real quick. So the way that I graph the derivative is I type it like this. Okay, I do math 8 and deriv ddx. I type the function I want to take the derivative of. It won't give you the equation, but at least it'll give you the graph of it. So x squared e to the 2x minus 3. And what you do here is you type x equals x. Now this is going to graph slow, but it will give you the derivative. So I'm just going to hit zoom 6. Ugh. And I need to change my window. I still can't see it. So I'm looking for where this is the derivative. So I'm looking for the derivative changes sign. So I'm going to change my window. I'll make y really small so I can see it. So we'll go from -0.1 to 0.1. I'm making it really small because it's small graph. Might not be small enough yet. I don't know if you can see. Oh yeah, you can see it there. Okay, you can see it changing sign. It changes twice. Once at -1, it changes from positive to negative. So that means that's increasing to decreasing. That's a maximum of -1. 0, it changes from negative to positive. So 0 would be a minimum. You don't have the value of the function, but you can at least see that. I'll go find them just to verify it. So second calc intersect. We'll go find this one first, I guess. There should be 0. There we go. This 1e to the -6 means 1 times 10 to the -6. It's just a very, very small number. It means 0 when you see that. Second calc, we'll find the other one, intersect. And the derivative changes from positive to negative here. So this is your maximum or a local maximum. And it's -1, 0. Okay, don't worry about the y, right? This just tells you where the coordinates of the critical values are. Okay, so we had 0 and -1 as critical values. All right, so so you use your calculator to find the critical value. So I'm just saying, hey, pretend this is the derivative. Oh, wait a minute. Yeah, okay, so I'm going to type it in my calculator. I'm looking at the derivative, not the graph, but the derivative. All right, so we're going to type the derivative. I'm going to leave that in there. Let's see, x squared minus 7x plus 10. And I'm going to raise it to the 1/3. So this is the derivative. So using the derivative graph on the top, find the zeros. So first thing I'm going to do is find the zeros because those are critical values, right? So I'm going to graph it. Oh, I got a weird window. Let me break out of that. Hit zoom 6. There we go. Okay, I see 2 critical values, one at 2 and one at 5. I'm going to go verify that. Second calc intersect. Enter, enter, enter. So 2 and I think 5 is going to be 0. I'm just going to look at it this way. 1, 2, yeah, 5. So 2 and 5 are my critical values. 2 and 5. Okay, these are the critical values, okay? Because that's where the derivative equals 0. Something that looked like this. This was 2 and this was 5. Graph the bottom. There's no bottom. Never mind that. If there were a bottom, you could graph it like if you had a fraction, like x plus 6. I don't know what you would have on the bottom, but you're gonna, let's say, I'm wondering if they meant that they wanted me to take the derivative. It's not a rational function unless I take the derivative. Yeah, let's do that. Let's pretend this is an f prime. I'm pretty sure this is what they want. This is f. So we're going to go ahead and we're going to find the derivative. Sorry about that. There's a prime there which shouldn't be there. Okay, so if I take the derivative, it's 1/3, whoops, times x squared minus 7x plus 10 to the negative 2/3 times the derivative of the inside would be 2x minus 7. Now I'm going to rewrite this. So this is 2x minus 7 times x squared minus 7x plus 10 to the 2/3. All right, so the critical values happen where the top and the bottom equals 0. So if I graph the top, I mean, I could do that. I could also just, it's 2x minus 7, so it's not all that difficult. But if I set that equal to 0, well, heck, I'll just do it. All right, I graph that. And it crosses the x-axis. You can verify that that's going to cross at 3.5. So that would be a critical value. Now, the bottom looks complicated, but I can just graph it and figure out when it equals 0. So I'm going to just graph x squared minus 7x, oops, plus 10 to the 2/3 and see where that equals 0. The 3 doesn't really matter. Doesn't do anything. All right, clear. X squared, whoops. The 1/3 isn't going to do anything either, but oh well. All right, x squared minus 7x plus 10 what power am I raising in that thing to 2/3? So you can graph the bottom and figure out where the bottom equals 0. There it comes. Okay, looks like the bottom equals 0 at 2 and 5. All right, and you can verify that on your own, but it's going to be 2 and 5. So these are all the critical values, right? So now the critical values are 3.5, 3.5, 2, and 5, right? Let's see. And now that I have those, I can just make my table. I didn't give you an interval of x, so let's say we wanted to go from 0 to 10. I mean, I'm just making it up. All right, so if we go from 0 to 10, you know, you go 0, 2, 3.5, and 10. And I'm going to test that in f of x. So that would be the original function, x squared minus 7x plus 10 to the 1/3. All right, I'm just going to type that in the calculator. Okay, that's pretty good. So then all I have to do is change this one little thing. Oops, I'll make that a 1. And that should do it. All right, so graph. I don't really care so much about the graph. I'm just going to go find the values. I'm going to use the table to help me get the whole numbers. All right, so f of 0 is 2.1544. F of 2 is 0. We'll get 3.5 separately. F of 10 is 3.42. And I need 3.5, so I'll just do it this way. Second calc value, and I'll type 3.5. And I get negative 1.31. Now that you have all this, right, pick the minimum. Here's your minimum, your absolute minimum, and here's your absolute maximum. Okay, so the calculator can be helpful, especially with some of the algebra. All right, make sure that, oh, there's the intervals. All right, make sure that you do check the endpoints, right, and plug the endpoints and the critical values. When you're finding absolute extremum, just go ahead and plug them back into the original function, not the derivative. Okay, that's the mistake, right? Because you use the derivative for sign tests, but for this you just plug it in. All right, so all right, so that's the end of that. So I'm going to stop this video, and there'll be a class assignment on this. I just couldn't find any Pearson homework that was relative to pulling out e to the x, so I just made up my own. So I'll put a Dropbox up there for you guys to turn that one in. All right, have a good week. Bye. The heck?